We do 2, 1, 2, 2, and we're finishing up 2, 3. Yeah.
Never mind, it's on the next section.
Okay. Okay, then so we'll continue on with 2, 3. The last example we looked at here was example 4. So we're simplifying this, I don't know, complex fraction, I guess. And what we did was we multiplied here on the bottom, below the dotted line, we multiplied through by the lowest common denominator to clear those fractions. We stated there was a hole at 0 because that's what h was approaching, our independent variable approaching 0, and then the y value approaching negative 8 over 81. So if you've taken pre-calc recently, this might look familiar, where you were setting up the difference quotient. So I don't know how many of you remember that. I'm sure some people do. But in previous classes, they would say, hey, here's the difference quotient. Find the difference quotient and simplify it. So that's what we're doing here with examples like this. We found the difference quotient, we simplified it, but in addition to simplifying, what we're doing is we're letting this h go to 0. And we'll see that this difference quotient and the fact that when h goes to 0 gives us one of the fundamental things of calculus that we talk about in chapter 3. But yeah, that's kind of based on the idea of the difference quotient. What was the difference quotient anyways? Does anybody remember? Like this thing right here. Like what is this?
Didn't it like calculate like the secant or like the secant? Yeah, the secant line.
Yeah, the slope of the secant line. So that's just the slope between 2 points on a graph, right? Because what we're not seeing in the bottom is we're not seeing this x plus h here minus this h right here. Sorry, this x. Ignore that. So when we have the x plus h, the change in our x values on bottom, then those x's just cancel out and you just get h. Right? So it's no different than when we computed like our s of a, our position at a, position at b, all over a minus b. That was just the slope of the secant line or the average rate of change, right? So whenever you computed a difference quotient, it looked kind of funky because you didn't actually have a number come out of it. But when you compute the difference quotient, it is the slope in this kind of setting. You have some sort of function here. And then your inputs are x and x plus h. All right, so if I said, what's the slope between these 2 points? You would first say, well, that's an f of x value. Or that value, rather, is f of x. The value here at this point is f of x plus h. So then we compute the change in y up top over the change in x on the bottom, which gives us a slope. So if you remember that, we will see that again once we start chapter 3. Anybody have any questions on what we've done in 2-3 so far? Okay. All right, so then we've looked at some algebraic methods, fractions, rationals, factoring. Those are really common. We're going to look at another method for this specific function, but it can apply to other functions as well. We're just going to use this specific one. And our function is x squared cosine 1 over x. And what we want to do is compute the limit as x approaches 0 on that. And we're actually going to look at a theorem that helps us sort of compute this, because when you look at a function like this, there is no radicals to rationalize. There's no factoring that can take place to help us solve that limit. It's not a fraction that we can clear out of the way and simplify. So like we're looking at a function that's already simplified as much as we possibly can. So we need another method for instances like this. And we're just going to take an aside for a minute and start off with something pretty simple, and then use that simple idea to like apply to functions, and then apply that idea in context of functions to things like this function f of x we're trying to consider here. So what if I told you I'm thinking of a number and that number is such that we'll call it n for the number I'm thinking of. And I'll tell you that the number that I'm thinking of is less than or equal to 10, but it's also greater than or equal to 10. What is the number I'm thinking of? What does it have to be? It has to be 10, right? N has to be 10. Does that seem pretty easy? Pretty straightforward? So all we're going to do is take that notion and apply it to function values instead of specific numbers. Let me just call this 1 and 2. Okay, so I'm going to say that the function f of x is less than or equal to g of x is less than or equal to h of x for every x value. So we're just starting off with that as a true statement. So if that's true for every x value, does it make sense to say that, so we'll say if this is true, then is the limit as x approaches a on all of these functions? Does that inequality still hold? Are we still able to do that? Is that still true? Yeah. Yes. Because we know this inequality was true for all x. Regardless of what x is approaching, we know that those functions are sort of in that order for any value of x, no matter where we are on the x, for x values. So regardless of what x approaches, just because of this statement here. All right. So what if we had that statement, and let's say we knew, so let's say we know that the limit as x approaches a on f of x is the same thing as the limit as x approaches a for the function h of x. And just for, just to be a little bit more, or less vague, I guess, let's just say that both of those are equal to some value, we'll call it L. So if we know that, what do we know about the limit in the middle? It's the same. It's the same, right? It has to be the same. So if we know that these two end limits, if you will, are equal to L, then the limit as x approaches a on g of x has to also equal L. Does everybody agree with that? I mean, intuitively, does it make sense? So that's what the theorem 2.5 here below, the squeeze theorem, that's what it's saying. So we've got three functions. The inequality satisfied for all values of x. And if the two end limits are equal to some number, that means the middle limit has to equal the same number. So they call this the squeeze or the sandwich theorem, because how this works out in practice is that these two limits here, we'll just say quote unquote, these are easy to compute. While the limit that's in the middle for the function g of x as they represented it, that this limit is difficult to compute. Oops, whoa, oops. The limit on the middle function is difficult. So, yeah.
So are there going to be cases where like the between like the outer I guess the functions and stuff, there's like a range of numbers for the middle that like say g could be like, will there be like scenarios where that would happen, or would there just be like a singular kind of like defining like middle?
Okay, right. So maybe write it out. So let's call this number m, like this. Is this what you're asking? Would this be the case?
Yeah.
Would that be the case?
Yeah,
yeah.
Yeah.
So you could certainly run into the issue where the function in the middle is bound between two numbers. So you could say, okay, well, I don't know what this limit is, but I know it's in between like 5 and 10, right? So that's perfectly okay. However, it doesn't answer the question as to what that limit is, right? So if I say this limit's between 5 and 10, you haven't answered the question what the limit is, right? You're just giving me this window at where the limit could be. So if this happens when you're using this theorem, you throw it away because it doesn't tell you anything. So what we're looking for, so we would just use another method. In a situation like this, what we're looking for when we use this theorem is that these two numbers on the end are identical. And when we have that, we know what the limit in the middle is. If that's what we're looking for, that answers what that limit is. So this, we would say, we would know here that the limit as x approaches a on g of x is also equal to m. So that's the situation we're concerned with. And I will say that it's difficult to establish relationships between three functions. Which one's larger, which one's in the middle, which one's smaller. And those will be given to you. You don't have to establish these inequalities. The most important thing here is to recognize how this theorem plays out and what it's saying. Okay, so we take this function that's difficult to work with, we put it in between two functions that are easy to work with, and then based off those two functions that are easy to work with, we infer what the function that's difficult to work with is, in the sense of a limit. Okay. Does anyone have any questions on this? We're going to use this to answer, we're going to answer this question. We're going to go back to this function here, x squared cosine of 1 over x, and use the squeeze theorem to answer what that limit is. Because on the surface, it appears that limit would probably be what? 0? Or somebody else? Undefined? So like if we just tried to plug x directly into this limit, what do we get? X squared is 0. And then we have the cosine of 1 over 0. So, but we got to remember that in the sense of a limit, we're not dividing explicitly by 0, right? We're saying that this turns into the cosine of 1 over a smaller and smaller number, right? So 1 over a smaller and smaller number in the sense of a limit would give us what? What?
An infinite value.
An infinite value, right? We kind of wrote that down last time. 1 over a smaller and smaller value is a larger and larger value, isn't it? So like this is 10, this is 100, this is 1,000. So these things just get larger and larger. Does that make sense? We're going to have to like think of limits this way too once we get into infinite limits, which is like the next section. So this is pretty much, you know, we'll just say this is the same thing as saying 0 times cosine of 1 over 0 is a larger and larger value. And as the inputs on cosine get larger and larger, what does cosine do? So just think of the graph of cosine. As we trot along this way on the cosine function, does it level off? No. If we went this way with the cosine function, it just does this forever, right? So remember, in the sense of a limit, it has to get closer to something. This isn't getting closer to something. It's true that it's in between 1 and -1 all the time, but it doesn't do this, right? It doesn't get flatter as we progress forward, if you will. So the cosine at infinity is actually something that doesn't exist. That limit doesn't exist. The first factor x squared's limit is 0. So how do we make sense of something where a limit's evaluating to 0 times something that doesn't exist? And that's what we're going to use the squeeze theorem for. So what we're going to start with, the fact that we know that cosine of anything, if I take the cosine of any argument, what do I know about that cosine by itself? We sort of just mentioned it in analyzing the limit for cosine. But cosine is always in between what? Yeah, 1 and -1. So it doesn't matter what we're taking the cosine of. Cosine of whatever is always in between 1 and -1. All right, so that's kind of our starting point for this. Other limits have different starting points, which is why I don't want you to worry about establishing an inequality, because those will be provided. But we're just going to start from scratch on this one. Okay, if I know that this is true, what I'm trying to do is I'm trying to establish an inequality to where this function in the middle is this function I'm trying to compute a limit on. So the only other thing that I need is I need to multiply this cosine 1 over x by the x squared, right? Then I have that function in the middle matching the function I'm computing the limit on, okay? So what we have is if we want our x squared here, let me just do this in a different color. If we want that x squared here next to cosine, which we do because that's our limit, in order to keep that inequality, we have to multiply the extremities by x squared as well. Okay. So we'll have a negative x squared over here and a positive x squared over here. So does that reasoning seem legitimate? Again, when you're asked on the homework or on the exam to compute a limit using this theorem, this inequality, such as this, will already be provided. You won't have to come up with an inequality all by yourself. Okay. So let's just check that. Remember, we don't necessarily need it to be true for all x values because we're just evaluating the limit as x gets closer and closer to 0. So we would hope that when we look at this visually, that as we get closer to the origin, it's pretty clear that these are this function and negative x squared and positive x squared are sort of the upper and lower bounds of that function in the middle. Oops. It's not what we're doing. There we go. Okay, so let's turn this off. We get a sense of cosine of x squared, cosine 1 over x. So it's one of those weird functions to where we start to see these oscillations closer and closer towards the middle. Let's zoom in a little bit. And then our function negative x squared and our function x squared. So we'll just focus here on the positive side. Even though those oscillations are getting smaller and smaller, we see that the function in the middle, x squared cosine 1 over x, is bound by negative x squared and positive x squared. So instead of asking or answering the question about the limit in the middle, the x squared cosine 1 over x, which is difficult to evaluate, as we saw it was 0 times something that doesn't exist, we're just going to evaluate the limit on the upper and the lower bounds. Yeah, question?
Does it kind of work as a leading behavior? Like that's how the majority of the function will work because of that variable?
Kind of, yeah. If you want to think of it as what did you say?
Leading behavior.
Like end behavior?
Yeah, leading or end behavior.
Yeah. So like it's sort of like trapping its behavior. I wouldn't necessarily maybe think of it as the end, because the end is usually reserved for infinity and negative infinity, but it's pretty much akin to that idea, yeah. So then we have this relationship established, and yeah, I'll point out, like, I think the next page I do have a note about how it sort of shows up on your homework, but once we get there, I'll let you know. So we have this relationship established. And then, of course, we're trying to figure out the limit as x approaches 0. So all we're going to do is apply that limit to all three of our pieces together. So then we have the limit, then the limit as x approaches 0 on all three of our pieces. So we're just ignoring that limit in the middle because it's difficult to work with. The limit as x approaches 0 on negative x squared is what? 0. So this limit is 0. We've left this thing alone, so we're just going to rewrite it. Sorry, this board is really, really scratched up. If something looks funny to you, just point it out to me. Is less than or equal to, again, the limit as x approaches 0 on the function x squared is also 0. So what is the limit of x squared cosine 1 over x as x goes to 0? What does it have to be? 0. It has to be 0. That's our conclusion for that limit. Again, we're looking at the graph we just looked at, probably was 0, but the graphs in that sense are super unreliable. Anyone have any questions on that?
If we're given something where we have to use the squeeze theorem, should we intuitively know that this needs to be solved with it, or would you go like use the squeeze theorem to solve?
Yeah, so I probably wouldn't say explicitly use the squeeze theorem, but when you see an inequality that's linking three functions, you should think squeeze theorem. So like for instance, on your homework, it says, first of all, the first part is, it says verify this inequality. So they give you that inequality, and then they're gonna have a couple of choices as far as the graph is concerned. Just graph it on Desmos or something else. I'm not gonna have you graph these complicated functions on the exam. So to verify the inequality, all we're gonna do is graph, and then we're gonna pick the appropriate choice, A, B, C, or D. Then once you verify that this inequality is true near x equals to 0, then we're gonna compute the limit as x approaches 0 for this function. Okay? And the way we're gonna compute this limit, again, notice that it's the function that's in the middle. So we're just gonna compute the limit of all three pieces, and hopefully the limit on the two ends are the same. So computing this limit, we would use the inequality. We're going to compute the limit at 0 because that's what we're asked to do. For this function on the end. And our other function on the end. So that's kind of how these problems show up. You know, that inequality is not intuitive at all. So they're just given to you, then based on that inequality, you compute a limit. So what's the limit as x approaches 0 on the function 1 minus x squared over 6? 1, right? Because the x squared over 6 approaches 0. So this whole thing goes to 0. We're just left with 1 on this side. And the limit as x approaches 0 on the function 1 is 1. Sorry, this thing approaches 0. Remember, the limit on a constant is always the constant. So this is also 1. Okay, so we would just say now then, based off of our work, that this limit is also 1. Initially, you have the same sort of issue, right? At 0, we have sine of 0 is 0, and the denominator is approaching 0. Remember, we sort of alluded to, maybe explicitly stated last time, in the sense of a limit, 0 over 0 can have any value. Because all it's saying is the top's getting smaller and the bottom's getting smaller. It's not saying that they're getting smaller at the same rate. Primarily where you see this, at least for us, is when there's these trig functions involved. Anyone have any questions or comments on that? It'll probably be an exam question with something like this, but it'll be like a short answer. Because, you know, really, these things should be pretty straightforward after we finish chapter 2. Just evaluating the limits on the end to determine the limit in the middle. So it probably show up as like a short answer question on the exam. Where it's like 2 or 3 points. Everybody okay with this? All right, so that's another method to evaluate limits. The last thing we're going to look at in this section is evaluating limits on piecewise defined functions. And just point out a couple of things here. So this is the function that's given to us. And computing a couple of limits here. The first one, the limit as x approaches 6 on f of x would be what? So as with any piecewise function, when you're asked about it, like whatever they're asking, generally you have to ask yourself, well, which piece am I dealing with, right? So if x is approaching 6, which piece am I using? The square root of x minus 1, right? And if you have to, just draw these individual domains out. Here's everything equal to 1 and less than 1. And this one's everything larger than 1. So yeah, if I'm asked to compute the limit as x approaches 6, 6 is completely contained within that bottom interval, right? I can approach it from both directions, and I don't have to worry about one-sided limits. Does everybody agree? I mean, just based off of this picture, hopefully it's super clear. So to compute this limit, we would just say, well, let's make it a little bit more explicit. That's the limit as x approaches 6, and we have to use this function. So that's just the square root of 6 minus 1 is what that limit is. What about the limit as x approaches 0? Yeah. So 0 is completely contained within this interval. I can approach it from both directions. I don't have to worry about a one-sided limit. Does everybody agree? So I'm going to use the top function to compute that limit. That's equal to 4. All right. Any questions? The thing you have to really be careful with when computing limits on piecewise defined functions are computing the limits at these endpoints that occur. Remember, all of this stuff right here in our piecewise defined function, all of that stuff is like the domain, but it's the domain for the entire function when we look at all of those pieces together. It's the domain of each individual piece when we consider of them individually. So anytime you're approaching in this specific example, anytime you approach 1, you have to be really careful, because as we can see with our domains that we've drawn out, those do entail a one-sided limit, right? I can only approach 1 from the right on the bottom function and 1 from the left on the top function. So even though this example 3 says compute the limit as x approaches 1 on f of x, you can't really compute that straight away. You have to break it down into these sub-pieces. I have to compute the left and the right limits first before I say anything about this two-sided limit. Does that make sense? Okay, so we're going to answer part 1 and 2 first. If x is approaching 1 from the right, what part of that function am I using? Square root of x minus 1. Yeah. We're approaching 1 from the right. That's the only piece I can approach 1 from the right on. Okay, so the limit as x approaches 1 on the right, we have to use the bottom function. So what would that limit be? 0? What do y'all think? 0? As x gets closer and closer to 1 on the right. So, you know, a lot of times it's helpful to draw these out. If I'm approaching 1 from the right, I'm approaching 1 through these values. They're all slightly larger than 1. We're saying, okay, any value that's slightly larger than 1 minus 1, and I take the square root of that, that hopefully it's pretty clear that it's going to get closer and closer to the square root of 0, which is 0. So the limit from the right is 0. The limit from the left, we have to use our other piece. So as the limit as x approaches 1 from the left, we we have to use the negative 2x plus 4. And so what do we get there? Positive 2. Does everybody agree? Okay, so first of all, what does that tell us about the two pieces of that piecewise function? Are they together or apart?
Apart.
They're apart, right? They don't connect. It's not the same y value here. So what would we say about the limit as x approaches 1?
Does not exist.
It does not exist, why?
Because depending on the, since from the left side it's 2, and from the right side it's 0, since they're not lining up at the same point.
Right.
The limit doesn't exist there.
Exactly. It doesn't exist because the limit from the left is not equal to the limit from the right. Does anyone have any questions on that? So this function in the middle here is just another example. If you were asked on a function like this, if you were asked to compute the limit at -3 or the limit as x approaches 2, you're going to want to look at those as one-sided limits because these are the two things that show up in the domain of that function. Anything else you can approach from both sides, any other number. So that would be just like those first two. You just determine which piece, plug it in, you're done. No two one-sided limits necessary, except for when we approach -3 and 2. Yeah.
So if we're given an equation of a line, and it's just one line, unlike that where it's two lines in two different domains, then there'll always be a limit. Not always, but there won't be a right-handed and left-sided.
Right. So for linear function, just like a regular linear function?
Yeah, it doesn't even have to be linear, but
Yeah.
necessarily just one line instead of two.
Right. One line instead of 2, you can always compute from both sides. Remember we looked at last class, we said that all linear functions and all polynomial functions we could evaluate just by directly plugging that value in. Of course, we have, even if both of these pieces are lines, like this one's not, but even if both pieces of your piecewise function are lines, you can't do that because it doesn't represent a fully connected line, right? Did that answer your question?
Definitely,
Okay.
thank you.
All right. Yeah, any other questions? Okay, in this example here, we're sort of illustrating or building upon those limit laws. And some of those limit laws did have caveats to them. But like I said, you kind of see that come out in practice. So we've got the square root of x minus 4. We're computing the limit as x approaches 4 from the right. So can we do that? Example I guess. Can we compute that limit? Yeah, how come we can do that?
Because it's just slightly more than 4, so then
Yeah.
so it's greater than, it won't be undefined, so it's not negative.
Right, exactly. The argument under the radical is that negative x is approaching 4 from the right, which means once again we're approaching, I'll go with it, we're approaching 4 through these values. All of these values are just slightly larger than 4. So when you take something slightly larger than 4 and subtract it from 4, you're not getting a negative under the radical. So what would that limit be? Yeah, 0. How about part 2? Exactly. That limit doesn't exist because you're going to end up with a negative under the radical. If we're approaching 4 from the left, all of these values are slightly smaller than 4. Anything slightly smaller than 4 minus 4 gives you a negative under the radical. So, whatever. Think of this as 3.99, etc., etc., etc. So this limit does not exist. Does that make sense? Does anybody remember what this graph of the square root of x minus 4 looks like? So what does the graph of the square root function look like? Right, yeah, like this. It's like this gradual curve like that. When I have a minus 4 in the middle, what does it do? Shifts it to the right. So if you saw the graph, this would all probably make 100% sense. Here's the graph of the square root of x minus 4. If I ask you to approach 4 from the left, there's no road, there's no function to approach 4 from the left on. But again, what we want to try to do is get familiar with some of these things that seem obvious when we look at a graph. We want to get familiar with looking at them, sort of analytically as opposed to visually. All right, any questions on 2.3? I think that's the end. Yeah, the end. Okay, in 2.4, let me see. And I think on this first page, yeah, on the first page we sort of get a precursor as what the next two sections are going to look like. Section 2.4, we're looking at infinite limits, and in 2.5, we're going to look at limits at infinity. So both of these limits sort of illustrate principles that you've already studied. We're just going to make them more precise with the idea of a limit. So an infinite limit is, let's write this out, and what we see here, in this specific example anyways, x is getting closer and closer to 0, and the y values are getting closer and closer, or getting larger and larger in the positive sense. So when we say infinite limits, what we mean is x approaches a finite number maybe we should say as x approaches a finite number, f of x or y approaches an infinity, positive or negative. It means the y values just get larger and larger in some direction. So does that make sense to call that a true limit then? What is it? What in order for something to have a limit, what does that mean? Just not even in a mathematical sense.
It stops.
Yeah, you gotta have a tops or a bottom, right? If I say the maximum temperature on a thermometer, whatever, it's probably 120 degrees, I don't know. But you're not gonna get a more maximum temperature. That's the limit of that thermometer, right? But if you had a thermometer that never ended, how could you ever say there's a limit to that, right? Does that make sense? Sometimes my analogies, I think, are pretty terrible. I don't know. Even though we're calling this an infinite limit, the limits don't exist because these functions, as we see, the function values aren't limited by anything. They just keep going forever in the positive or the negative sense, as indicated by this right here. So you don't actually have a limit in the sense of a limit, but we still call them infinite limits. So I hope that's not confusing. I didn't come up with the words. I'm just letting you know that these limits do not exist. But it's a little bit more explicit than what we said like the last time, right? If we said, hey, this limit doesn't exist, well, why does it exist? Are the two pieces not connected? Is it a limit like a sine or a cosine that never actually flattens out? Or does it not exist in the sense that the thing isn't actually limited, that it's approaching infinity or negative infinity? Specifically, in this case, when you come up with a limit as x approaches a finite number, and the answer is positive or negative infinity, it's going to always tell you a specific thing about the function. We just looked at this function 1 over x squared from an algebraic standpoint. Here at this x value of 0, what's happening to the function, or what does the function have? A vertical asymptote, more specifically, yeah, an asymptote, but a vertical asymptote. Does that make sense? So for like any function, if I say that whatever function, you're approaching some finite number, let's just say it's here. If I'm approaching this finite number from either direction, and I know that as I get closer and closer, the y values get larger and larger, isn't that the only option for what's happening at a on that function? Even if I approach it from this direction, and it does this, it gets larger and larger in the negative direction, the only outcome in either case is there has to be a vertical asymptote right there. Does everybody agree with that? So that's exactly what we're talking about in 2.4. Whenever you come up with an infinite limit, meaning the answer is infinity or negative infinity, you need to show it that way because it's telling you that you have a vertical asymptote there. If I just say, hey, this limit at a doesn't exist, there's a myriad of things that could cause it not to exist, right? The pieces might not be connected. It could be like one of those oscillating type functions. But in this case, if I compute this limit at infinity, my answer is one of these two things, then I know for sure on this function at a, I have an asymptote, a vertical asymptote. And that's exactly how vertical asymptotes are defined. So like in an algebra or pre-calc class, they would have said, well, a vertical asymptote is sort of this thing in the denominator that's left over after you've simplified, right? Like that's the best you got. But really a vertical asymptote is this right here. If you approach a finite number and your function values approach infinity or negative infinity, that's what it means to be a vertical asymptote. So those are infinite limits. Limits at infinity, the roles have kind of reversed. Now x is approaching infinity or negative infinity, and y is approaching a finite number, or the limit is approaching a finite number. So we're saying that these limits are illustrating the fact that as x approaches or a positive or negative infinity, again, meaning x is growing arbitrarily large in the positive or the negative direction, y or f of x approaches a finite number. That's a limit at infinity because x is approaching infinity. Do these limits exist? Yeah, but even though x is getting larger and larger, y is approaching something specific. So these limits exist. What do these limits tell us?
Horizontal asymptote.
Right, good. Horizontal asymptote in behavior. So these limits exist. I mean, when they exist, of course, these limits exist and describe end behavior. So you can, all functions have an end behavior, even if they sort of taper off to infinity, that's still descriptive. If I'm way out here on this function and it approaches infinity, that's fine. I know like way out here that the function's pointing up, right? Or I know way out here that the function's pointing down. Like, so we can describe end behavior. And you might remember end behavior from like the leading term test on polynomials. Does anybody remember that? Sort of, like you had 4 outcomes with polynomials. We'll talk about it, but it sort of was like where you draw something like this, right? Do y'all remember doing that? Or sometimes they had these squiggles in there. Like that was the end behavior of a polynomial where you use the leading term test. hey, what's the degree and what's the leading coefficient? There was there was end behavior on rational functions, which was the case that, if the degree of the numerator is less than the degree of the denominator, then you got a horizontal asymptote at y equals to 0. Do y'all remember that? That's the end behavior on rational functions. So in general, not all functions have horizontal asymptotes, but all functions have end behavior. And the way we describe that is we just compute the limit as x approaches infinity. Okay. So that's what we're seeing in 2.5. More or less how to describe and define a horizontal asymptote. And in 2.4, we're seeing how to define a vertical asymptote. Anybody have any questions? All right, so 2.4. Infinite limits. They're just defined sort of mathematically in the words we just stated. So I wouldn't focus too much on the actual jargon here. But we're looking at either case. As x approaches a finite number, the y values are getting arbitrarily large in the positive direction and in the negative direction. But notice this qualifying statement here. It says, in both cases, the limit does not exist. So for these types of limits, don't just write does not exist. It's not explicit, right? If once we write something that doesn't exist, then the question is, okay, well, why doesn't it exist? In this case, we say the limit doesn't exist because the function values are getting larger and larger. And when we say that, we automatically know there's a vertical asymptote there. So it's a little bit more descriptive. The difference is sort of subtle, though. I hope everyone's clear on that. Because a lot of people will just put doesn't exist on the exam, and that's, it's technically incorrect. Okay, so these limits don't exist. But they do describe, the definition. They do describe vertical asymptotes. So those figures didn't. So somehow those figures didn't print. So let me grab these figures, just if you're going to refer to these later, so we're not. Oops. So we're just not referring to something that's not there. For A and B. Just bear with me. Okay, so that's what they're referring to here in the two-sided definition. So notice in either one of those cases, since the limit from the left and the right are both approaching the same infinity, if you will, they're both positive in A and negative in B. We say that limit is positive infinity for A, and we say it's negative infinity for B. But if you can remember, some rational functions like this one we drew out on the board do have different behavior as you approach A. Not all the time do they kind of die off in the same direction. So that's where this notion of the one-sided limit comes in, and then these figures that they're referring to. 226. Yeah, these four. Okay. So honestly, in some ways, like the way you analyze these things algebraically was a little bit easier. Hey, where's my function on the left or the right of the asymptote? Like you just plugged in some x values to see what the y value was.
So in some instances, it's a little bit easier to evaluate these things algebraically, but what we're doing here is it's more precise, it's more technical in how we're describing this stuff. Okay, last one. All right, so again, technically, all of the time you're approaching a vertical asymptote, you do need a one-sided limit. Because a vertical asymptote is essentially taking like your XY coordinate system and tearing it into pieces. Wherever that vertical asymptote is like a different piece. It's no longer is your XY coordinate system connected. So you always have to approach these things from both directions. It's just in the sense of as we approach A from the left and from the right, if both of them are positive infinity, then we would say that this limit here is infinity or negative infinity. But we were always computing the one-sided limits. Sorry those didn't print off for you. Does anyone have any questions on this? So we'll look at maybe one or two examples and take a break. So let's look at this through like an algebra lens, and then we'll look at it through a calculus or a limit process. I think remembering stuff about functions using an algebraic approach is really helpful, because if you look at a function like this and you're asked to compute a limit, let's say, you're looking at that and like, oh man, I have no idea. Like, I just really don't know what to do. If you can remember, ignore the limit and just look at the function. What kind of function is that? What do we call those? Rational functions. So if I'm computing a limit on that, and I'm clueless, I can just say, all right, well, I'm dealing with a rational function. What does algebra tell me about rational functions? What do we know about the function 5 plus x over x?
Can be simplified.
It can't be simplified, right? So what does that mean?
No holes.
There's no holes, right? There's no holes in this function. Where is this function's vertical asymptote?
Where x is undefined.
When x is 0, right? So now, with that knowledge, I could say, well, if someone asked me to compute the limit as x approaches 0 in this function, there's an asymptote there, right? So I should compute the limit from the left and from the right. I know that there's already an asymptote. I don't even know what this function looks like, but I know that there's an asymptote here. I do know that much. Does everyone agree? So it can sort of help you out with evaluating limits. I don't think it's cheating, it's just using prior knowledge. Okay. Then the question was, well, what does the function look like? As I get closer to this asymptote from the right, I've got two options initially. First option is my function is going to follow up that way in the positive infinity, or it could be down here at negative infinity. Does everybody agree? That was just sort of where you were once you identified. And as I approach from the left, again, the function could be up here, oops, that's supposed to be straight, or down here. Where was it? Well, you had to test points on either side, right? You had to say, well, over here, I'm going to pick an x value, let's say, I don't know, I'm going to pick an x value of 5 and just plug that into my function. That gives me 10 over 5, which is 2. That gives me an actual point right here. So the thing has to be up here. It can't be this thing down here. And then we did the same thing on the left. I don't know, pick a value like -3. -3 into that function gives me a positive over a negative. So it has to be this one down here. It can't be this one. Does everybody kind of remember that?
So that was the algebraic approach. I'm gonna make a note here. The calculus approach, we would say, well, this function is clearly not defined at x equals to 0. What's happening at x equals to 0? I'm going to compute the limit as x approaches 0 from the right and from the left. It's going to tell us the same information that we had, but since we're in a calculus class, we need to reason through it this way as opposed to an algebraic way. Again, use the algebraic way to sort of solidify in your mind what it should be, so you have an idea of where you're going. But we need to be able to analyze these limits just as efficiently. So again, the problem, as was pointed out, this isn't a function that we can use the conjugate. You can't factor anything out. You can try to squeeze it in between two functions. It's going to be pretty difficult to do that. So this is where the knowledge of, hey, that's a rational function and x equals 0 is a vertical asymptote really pays off, because we know that's a vertical asymptote just from an algebraic standpoint. This thing can't be reduced anymore. I don't need to figure out what form of 1 do I need to multiply that by or anything like that. I recognize that that's a vertical asymptote that I'm approaching, and so the way I analyze that limit is kind of how we analyze that x squared cosine of 1 over x. If x is approaching 0, what does the numerator approach? If x is approaching 0 from the right, rather, what does our numerator approach? Not the numerator, just the numerator by itself. 5, right? Does everybody agree? There's no issue with the numerator. The issue is with the denominator. What's the denominator approaching? 0. So here's the thing. We have to know what values of 0 it approaches. Like I could have a function as I approach 0 from the right that's doing something like that, or a function as I approach 0 from the right that's doing something like that. And it totally matters what values you're approaching 0 through. This one, I'm approaching 0, yeah, but all of my y values here that I'm approaching through are positive. All of the y values I'm approaching 0 here through are negative. And that absolutely matters. So it's clear here that if I'm approaching 0 from the right, then I'm approaching 0 through positive values. There's usually not a standard agreed upon notation for this. I usually just indicate it this way. Other people will just write this. Like some people I just see like put SP for small positive. There's no agreed upon notation, so whatever makes sense to you, write that. So the numerator is approaching 5, but the denominator is getting smaller, excuse me, smaller and smaller through positive values. So what is our quotient? 5 over smaller and smaller positive values approach? Infinity, right? 5 over a smaller and smaller positive number is a larger and larger positive number. So I'll just write this. It's kind of redundant to write positive infinity, but I'm going to go ahead and write it. So that's how we should get accustomed to analyzing those. Again, you can default back to your algebra to make sure, but I need to see like something. I need to see something like this or something like this, because as you go on, if you have to go on, it's important to know like a finite number over a smaller and smaller number is infinite. That's an important concept to know. We can default to our algebra to see, well, was that actually correct? I don't know, from the right of 0, let me plug in a positive number, the function's up here, the arrow has to be up here. So as I approach 0 from the right, the function is approaching positive infinity. Like we already verified that, but now we're verifying it without really looking at the graph. So then we have a similar analysis here we've got the numerator as we approach 0 from the left. The numerator still approaches 5, but this time the denominator is approaching 0 through negative values. So now we have positive 5 over smaller and smaller, or negative values, which would make this what? This limit would be, right, negative infinity. And even if we didn't know any of this, like let's say we just totally forgot algebra, but this process seems pretty simple. Maybe it does, maybe it doesn't, but let's just assume that this seems pretty simple. Now, based off of this, I have my result. I don't know what my function looks like in totality, but I do know that as I approach 0 from the right, that the y values get larger and larger. And I do know as I approach 0 from the left, the y values get smaller and smaller. So it probably looks something like that. I'm not 100% sure because I actually haven't done any work to tell me what's happening over here. And I haven't done any work to tell me what's happening over here. But I know that this is exactly what's happening as I get to 0 based off of my limit. And then I would say, well, if my function's sort of repelling at these lines, then that has to be my vertical asymptote right there. So the other way is sort of looking at this in reverse. If this is a result of your work, you should be able to absolutely look at that work and say, all right, well, since that one's negative infinity and that one's positive infinity, the function 5 plus x over x has a vertical asymptote at x equals to 0. That's what all of this work is implying. Is that clear? You should be able to look at it forwards and backwards, if you will. Does anyone have any questions on this? Yeah.
Will we be given like an infinity over infinity or 0 over 0 yet?
No.
Okay.
If you see a 0 over 0 or infinity over infinity, you need to do some algebraic work to simplify that, like the ones we looked at in 2-3, with like complex fractions, conjugates, or factoring.
Thank you.
Yeah, you're welcome. When we talk about derivatives, we can talk about L'Hopital's rule, which makes sometimes not these, but it makes a lot of other limits a lot easier to evaluate. So.
Yeah. Glad I don't think about it again.
Yeah. Any other questions? All right. We'll look at a few more examples after break, but that's the basic idea that we're going to sort of build on after we come back. All right, so with that being said, we have the definition, the formal definition of the vertical asymptote. And you'll notice again that it's defined in the same terms that we've been speaking of. Okay. So hopefully after talking about it, looking at an example, that it totally makes sense as to why a vertical asymptote's defined that way. If that's the case with your limit, that's the only thing that can be happening on your function. We already looked at these two. Let's look at a couple more straightforward ones, and then we'll look at one that's a little more involved. So like if you were asked to compute the limit as x approaches 0 and 1 over x squared, don't just say it doesn't exist because you end up dividing through by 0. That's not the case. It's true that this limit doesn't exist, but you need to be a little bit more descriptive to me and yourself as to what's happening on this function. Okay, so we should know just by looking at that function that, yeah, it's going to have a vertical asymptote at x equals to 0, because that factor of x doesn't go away, right? It doesn't reduce out. So as we approach 0 from the right, we're going to look at this the same way. The numerator approaches 1. The denominator approaches, positive values that are getting smaller and smaller, but this time we're squaring those. So this limit approaches positive infinity. Does that make sense how we're looking at this? Does anyone have any questions or need clarity? Yeah.
Just heads up, what you put online does not have pretty much where we talked earlier. After the figure 2.6,
Yeah.
2.26, none of that is online.
None of it's online?
I just verified that.
Sorry, y'all, I don't know why it's been, like, I'll pull up notes on my computer and they'll be totally filled, they'll be totally ready to go. And then when I open them somewhere else or upload them clearly, it's just not coming out. All right, I don't know that there's anything I can do about that right now. If you see anything like that in the future, if you are printing those out, please let me know. I'll try to go through them, but it's kind of time consuming. And I just assumed the technology would work, so that's my fault. Okay, so and then we've got a similar situation as we approach 0 from the left. The numerator is still approaching 1. Denominator, we are approaching 0 through negative values, but those are also being squared. So those negative values, they are still getting smaller and smaller, but they're all being squared, which makes them positive. So I'm just going to write this again as 1 over positive 0 without any other operations, and then write that that's infinity. Again, numerator's fixed, denominator's getting smaller and smaller, so the quotient gets larger and larger. That's all we mean when we write this stuff out. I'm not saying divide by 0. Is everyone clear on that? That's never the case with limits. So in this instance, what should we say about the limit as x approaches 0 of 1 over x squared?
Infinity.
We can say it's infinity, but we have to sort of look at it as part 1 and 2. As far as what's happening visually, what we know is as we approach 0 from the right, the function's up here, and as we approach 0 from the left, the function's up here. They never actually touch, of course. So based off of that work, we've got this diagram, and we know that x equals to 0 is a vertical asymptote. And we'll just write that there to get used to looking at it. I'll just abbreviate vertical asymptote. Now, you could see like a really weird function where like from the left it's 5 and from the right it's infinity. Just know that if either one of those limits from the left or the right is ever an infinity or negative infinity, you're going to have a vertical asymptote there. We don't see functions that have a vertical asymptote on one side and something else on the other, but one of these limits, the one-sided limits being infinity, is enough to tell us that. The reason we look at it from both sides is so we can have a sense on what's happening on both sides. But we could have stopped at part 1 and said, hey, well, that's enough to tell me that I have a vertical asymptote at x equals to 0. Does that make sense? All right. Anyone have any questions? So I just kind of noted that here. When we write this thing, we're not saying we're dividing through by 0. We're just saying that the denominator is getting smaller and smaller through positive values or smaller and smaller through negative values. We see this weird type of stuff with limits as we revisit them later as well. So I'll give you all a chance to copy that down if you want. And I guess we could put a note here in both cases. The limit is infinity or negative infinity. Does anyone need more time with that? Yeah, I guess we can look at this one as well. It's kind of similar to what we looked at that last example. But this might be how it's initially presented to you. Compute this limit. And again, the way I would try to get in a habit of looking at these things as well. Okay, maybe the numerator factors, maybe it doesn't. But when I look at this initially, clearly I have a problem in the denominator, right? My denominator is approaching 0. As we saw in 2.3, as opposed to what we're seeing here in this section, just because your denominator approaches 0 doesn't mean that you're going to have an infinity as a result, right? In 2.3 we saw many examples where those problems of the denominator approaching 0 were factored out basically, and we ended up with some finite number. Okay? So just because initially your denominator approaches 0 doesn't mean you're going to have an infinite limit. So the strategy here is, I guess there's two things we could do. We could say, well, how could the numerator factor? And if it does factor, is it going to get rid of the x minus 2 squared on the bottom? No, clearly the top is an x minus 2 quantity squared. So at best, if we factor the numerator, you get rid of one of those. So let's just look at it the way we've been looking at these. Let's compute the limit as x approaches 2 from the right and from the left. Because we suspect that that's an asymptote in the sense that the numerator isn't the difference of squares or a binomial squared, right? So you need to know information about both numerator and denominator, right? Like if your numerator is approaching a negative number and your denominator is approaching 0 through negative values, then you've got a negative over a negative. So you've got to be mindful of what the numerator's doing and the denominator's doing. As x approaches 2, the numerator approaches what? I'll just rewrite this here. Positive.
Positive 6.
6. Maybe the number itself is kind of irrelevant. It's kind of the sign that we're after, but go ahead and compute that. We've got what is this, 2 and for x, we've got a minus 18, and the 20, that's a positive 2, and 4, that's a 6. The numerator is approaching 6. Denominator approaches what? 0 through what values? Positive, right? Because that entire quantity is being squared. So even if what's in parentheses was approaching through negative, doesn't matter, it's getting squared, it's approaching positive 0. There's 0 through positive values, rather. So this limit would come out to be, we've got a positive number over a positive small number, it's positive infinity. got a similar thing here with the limit from the left. Kind of like the last one, I'll write this out. This is actually inside the parentheses, of course, since we're approaching 2 from the left, those values are slightly smaller than 2. Any number slightly smaller than 2 minus 2 is going to be a small negative number. And then we've got that squared, which again is this. So, you know, if you like that notation, use it. If there's a notation that you would prefer, it doesn't matter what notation you use. Again, we could have written this one out as 6 over a small negative number that's being squared. It's equally as efficient, I think. So like that other one, we could say that this limit is infinity, but we've got to keep in mind the context, right? We've got a vertical asymptote at x equals to 2. So we have our plane separated into 2 pieces. It's just that both of them are going to infinity. Anybody have any questions on that? So we'll compute this limit next. And really, the approach that we took in that first one was sort of, I would say, a little bit careless. Just like when you're presented with a function like this in an algebra or pre-calc class, the instructions or the recommendation or whatever was always factor the numerator completely and factor the denominator completely. So I would still recommend doing that. If you're computing a limit on a rational function, try to factor the numerator and denominator completely. You'll see here, as x approaches 2, initially looking at that, you might say, well, 2 in the bottom is going to cause me to divide by 0, therefore that limit is going to be infinite. But like we said, just because the denominator approaches 0 doesn't always mean that you'll have an infinite limit. In this one, what happens with this limit?
Exponents are exponents, too.
Right, the top, the function on the numerator is x minus 3 times x minus 2. So these two factors divide out. So that problem of dividing through by 0, if you will, sort of got canceled out. We don't have an issue with the denominator anymore. We're just going to plug 2 directly in for our x's. So we have -1 on top and +3 on the bottom. So what does that mean for us? What happens on this function?
There's a hole in 2.
There's a hole, right? We approached a finite number. As x approaches a finite number, y approaches a finite number. The original function wasn't defined. Clearly, it wasn't defined at 2. We've got a hole. This function is a hole. At that location. What we did see remaining, once we simplified this algebraically, we did see the x plus 1 remaining. So just from an algebraic standpoint,
hopefully we would know that there's a vertical asymptote on that function at x equals to -1. Does anybody have any questions on this? So make sure you factor first, just so you're totally clear as to what's there, if you will, and what's not. We're going to compute the same function. We're going to compute the limit as x approaches -1. Well, since we already factored it, we'll just leave it like this. So honestly, before we even compute the limit from the left and from the right, we can just work with our simplified function because, no matter what x is approaching, that function will simplify to x minus 3 over x plus 1. So maybe redundant to write this down again since we've seen how it simplifies. But nonetheless, we've got this factor on the bottom that causes the bottom to approach 0, and that factor cannot be removed. So now this is where we have to compute the limit from the left and from the right. So to evaluate this limit, one-sided limits are involved. So we're going to look at both of those. As x approaches -1 from the right, what is the numerator approach? What? -4, right? That doesn't change in either case. That's not the problem. X approaches -1 from the right, the denominator x plus 1 approaches what? As we approach -1 from the right. So if you have to, just to think about it, just draw it out. Here's -1. I'm approaching -1 from the right. Numbers that are slightly larger than -1 get added to 1. What is our denominator? We know it's going to be 0, but we have to know what values of 0 is it approaching through. Is it positive or negative? Sorry.
Positive.
Positive. Do y'all agree?
Yes.
Negative, think about this as -0.99, etc., right? Those are all the values we're approaching through. All of those types of values, when we add them to 1, they're still slightly positive, right? So this limit would be what? Negative infinity, right?
That's right, yeah.
Yeah, because the negative up here, it doesn't matter what we approach 0 through on the bottom. That doesn't solely determine our infinity. It's the entire quotient. You've got a negative number over a small positive number. That's a small. I get large negative number. This is negative infinity. So maybe seeing this, it's like it's super tedious. Can I just go back to looking at our rational functions through an algebraic lens? It was so much easier, right? Okay, so negative infinity from the right and from the left. As we approach -1 from the left, x plus 1 approaches what? Yeah, 0 through negative values, right? Because now we're over here approaching this way. So it's like -1.99, etc., etc. Added to 1 gives us a small negative number.
So that, the overall limit would be positive infinity. You got a negative over a negative, that gives us the positive, and the denominator approaching 0 gives us the infinity. So both signs up top and bottom give you the sign of the infinity. The denominator approaching 0, while the numerator is fixed, gives us the infinity part. So again, just kind of a quick sketch of this. We've got a vertical asymptote at -1 because our limits are infinity. So -1 here. Oops. Vertical asymptote. As we approach -1 from the right, we have a negative infinity. So down here. And as we approach -1 from the left, we've got a positive infinity. So, you know, whatever else the graph is doing, we need other stuff to tell us that. But we do know that's where these arrows go. X minus 3 over X. So is that kind of what we drew? Yeah, that's what our work showed us. All right, do y'all have any questions?
If you weren't evaluating that from the left to the or to the right, what would its behavior be? Just its normal behavior, its limiting as it goes to -1. What does it have one?
So yeah, if we were to ask the question, what is this limit? The two-sided limit.
It is an asymptote.
Yeah, we wouldn't say that there's a limit. Like the last two, where it was approaching, both sides were approaching positive infinity. We could technically say that it was infinity in those two instances, but since they don't match up, they're both not at positive or negative infinity. This limit wouldn't exist. So like this limit doesn't exist, but in the sense that we say this, we say, oh, well, there's an asymptote here, so there has to be something happening on both sides. This is when we would then look at all of that stuff above.
Got it.
To get a clear understanding as to why it doesn't exist.
Double check.
Yeah.
Thank you.
You're welcome. Any other questions? You can also use this idea to look at our trig functions too. We kind of look at them in the same light, you know, like, I guess I probably should admit it, but I personally don't really remember like cotangent graphs and cosecant graphs. Like, you know, I should memorize them at this point. But the way I always look at them are by looking at them in terms of the sines and cosines. Like if you know sine and cosine, the graphs, how those things behave, then all of the other 6 trig functions are built off of those two. So really, you need to just know sine and cosine. Any information about the other 4 trig functions you can get from sine and cosine, and your knowledge of like rational functions or whatever. So if we have to evaluate the limit as x goes to 0 and cotangent of x, let's first of all think of cotangent in terms of sine and cosine. Cotangent is what?
Cosine over sine.
Cosine over sine. So we'll think about it as cosine over sine. So then we ask ourselves, are there issues? Well, as x approaches 0, cosine approaches what? From either side, cosine approaches 1. Right, let's draw these graphs out to remember. Oops. There's cosine, sort of. And we'll put sine over here too. Yeah, good enough. So we're gonna keep these in our mind. This thing, the top approaches 1, the sine of x approaches, well, I mean, initially we might say it's 0, but it's not totally clear, right? Sine does approach 0, but notice it depends on what side of sine I approach, right? So I could say that it approaches 0 from the right. As I approach 0 from the right, it's positive values. 0 from the left, it's negative values. But like that aside, 1 over 0, what would that give us in terms of a limit? It's positive infinity. So we would say, all right, well, clearly we have an issue on cotangent at 0, right? The function values are blowing up near 0. So we then need to look at it as 2 pieces. What happens as I approach 0 from the left and from the right? And we do that the same way. We're going to think of this, oops, sorry. Got a little careless with the notation. So that being said, I'm going to just put a new page in here so people watching at home know what we're talking about. On the exam, if this is a notation issue, and I think it's super important. On the exam, if you have a limit like x plus 3 times x minus 1 over, let's say x plus 2 times x minus 1. If like this is something in your work, and then you say that this is equal to this, and that's equal to this, please try to avoid those errors where you're eliminating the limit, because this function is equivalent to this function. But then when you write that this thing is equal to 4/3, like that doesn't make any sense. That function's not equal to 4/3. That function's only equal to 4/3 if x is equal to 1, or if it's the limit as x approaches 1 in front of it right here. So I know it's like a really minor thing, but it's a really technical thing that you should avoid. So if you don't like writing the limit over and over and over again, then take whatever function you're given, just take it off to the side and work it like it's an algebra problem. And then when you're done simplifying or reducing, then put that function in front of your limit to compute your final limit. Because I get it, writing the limit over and over is tedious, especially if the function reduces and reduces and reduces. But it is a very technical thing that you shouldn't forget. I probably won't take off points on the first exam for like dropping stuff like that, but I think later, exam 2, 3, and the final, I would take off points for it. So, just try to remember that. So I'm not trying to be difficult. It's just, if certain things you write without the limit don't actually make sense. So, anyways, we'll go back now. And I said that because I forgot to write this limit here. So this limit as x approaches 0 from the left, we're going to think again cotangent as cosine over sine. We already know there's not an issue with cosine. Cosine approaches 1. Now we do have to be careful here and specify as x approaches 0, let me write it like this, as x approaches 0 from the left, what does sine approach? 0, but through, good, yeah, negative values, right? Here's the sine function. I'm approaching 0 on the left. These are all negative values. So what's that limit? Negative infinity. Positive 1 over negative gives us a negative, and the denominator approaching 0 gives us the infinity. Are there any questions on that? So I may not remember what the graph of cotangent looks like, but I know for sure that on the left-hand side of 0, the thing's dying off to negative infinity. Similar thing here. Approach, let's do this. We'll just do this. We're approaching 0 from the right on sine, approaching through this direction through positive values. So this one would be 1 over small positive values. Okay. Which of course is a positive infinity. And if you get stuck with other trig functions, think about them in terms of sine and cosine, and hopefully you remember those. So we'll go ahead and just put the graph of cotangent in just for visual verification. At least this part. Spaced out here. Just leave it right there. But that does verify, as from the left, we said it was negative infinity. We can see that from the graph. Negative infinity down here. From the right, it's positive infinity up here. All right. Do y'all have any questions on any of that? Yeah.
So is the original answer?
Yeah, right. So then we could, since these infinities don't match, we would technically say that this limit doesn't exist. But again, we're being more specific than saying it doesn't exist, because we're actually, with part 1 and 2, we're showing exactly why it doesn't exist. So we'll get rid of that. Just say this doesn't exist. Any other questions? All right, then, so one last thing we're gonna mention here in this section is this, we're gonna work this example here. We're gonna be given the function x to the 1/3. And the first part, we wanna find the slope of the secant line through the point 0 and h comma f of h. So the point 0, 0 is on the graph of x to the 1/3. And it's a generic way to give a point, but we'll kind of look at the graph and talk about why, I guess. The point h, f of h, just means plug h in for x, right? So we're going to plug in h for x, and f of h is just actually h to the 1/3. So we're making things a little less ambiguous. That's really what the instructions could have started off saying. I don't know why it didn't start off saying that. I got this from our book. So that's what we're dealing with. Find the slope of the secant line through those 2 points. How do we find the slope of a secant line through 2 points? Yeah. So then here for us, what would that look like? M secant, the slope of the secant line. It's just the slope between those 2 points, right? It's the change in the y values over the change in the x values. And that of course is just h to the 1/3 over h. And then we'll simplify that a bit further. H to the 1/3 over h is really what?
Cube root of h.
The cube root of h? Yeah. So the top is the cube root of h. Yeah. What is the cube root of h over h equal to?
The square root of h.
The square root of h. No, not the square root. We wouldn't change the roots here.
Will be h to the negative 2/3.
Right, yeah. So properties of exponents, we just subtract h to the first. We subtract the numerator from the power of the numerator from the denominator. So that's h to the 1/3 minus 1 power. Y'all remember? Which is h to the negative 2/3. So h to the negative 2/3, remember, is also 1 over h to the positive 2/3. Which is also the same thing as writing 1 over the cube root of h squared. So however you want to represent that, h to the negative 2/3, 1 over h to the positive 2/3, or 1 over the cube root of h squared. I don't ever really have a preference. They're all acceptable. So it says on the graph of x cubed, we'll plot this in a minute, but does anyone remember what the cube root graph looks like?
It's like a horizontal x cubed.
Yeah, it's like a horizontal x cubed. We're just kind of using this as a reference to talk about what they're saying. They're saying find the slope of the secant line on this point, and h is just some value, right? H is over here, maybe h is over there, whatever. H, just think about h again as a distance from 0. There's f of h. So all we did was find the slope of the line that connected those 2 points. Okay, can't really do anything with that. It just represents a slope. So then part B, we're going to say calculate the slope of the secant line as h approaches 0 from the right and as h approaches 0 from the left, and interpret the results. So if h approaches 0, that this second coordinate is approaching the first coordinate, right? So that makes this second coordinate approach the first coordinate. And again, from the left and from the right, just indicates that h could be to the right of 0, or h could be over here, which we might call negative h. This is h approaching 0 from the left, if you will. Okay. So there's the slope of our secant line, 1 over the cube root of h squared. We're just going to compute this limit. 1, what's the limit as h approaches 0 from the right on the slope of our secant line? So we have to compute that limit. So the limit as h goes to 0 from the right on 1 over the cube root of h squared, what would that give us? Positive 0 on the bottom, right? The numerator approaches 1, regardless of what h approaches. Yeah, h is approaching 0 through positive values that get squared, and then we take the cube root of that, right? So that's still positive values. You know, just to add another layer of complexity, that 1 over h to the 2/3, the root has to stay as is, but remember that power on h could be applied to h first, or we could apply that after we apply the root. Doesn't really matter. So maybe it's easier to think about, well, the denominator is just the cube root of h quantity squared. Regardless of whether that comes out to be positive or negative, since we're squaring it, it's still always going to be positive. So infinity, everyone agree with that? And we see that as we compute the limit as h approaches 0 from the left on the slope of our secant line. I have a similar thing. The small negative values are being squared, so now there's small positive values. Taking the cube root of that doesn't change, so it's still small positive. So that overall limit is infinity. All right. Any questions on our limits that we've calculated? Then we want to interpret what is that actually telling us. So the first thing to remember is that, yeah, by itself a limit's just a limit. Typically it's tied to something. The limit we're actually computing here was tied to the slope of the secant line. So what did we look at in 2.1 when we took the slope of a secant line and then started computing a limit on that? Or looking at the slope of the secant line over smaller and smaller time intervals, the slope of the secant line actually approached what? Yeah, so like more general. It ended up approaching 64, right? But more generally, what was 64?
Finite number.
It was a finite number, and in that particular example, it was our instantaneous rate of change, right? Do y'all remember doing those? So like, if you compute a limit on, if you take a secant line and look at it over smaller and smaller intervals, meaning that there's a limit attached to a secant line, the slope of the secant line rather, what does it turn into?
Tangent line.
A tangent line, right? It's the slope of the curve at a single point, not at 2 points anymore. If I make these 2 points close enough to each other, aren't I just computing the slope of the line at that single point? So we said the average rate of change in that 2.1, the average rate of change over smaller and smaller intervals, which was a limit, the limit on the average rate of change gave us an instantaneous rate of change. The limit on a secant line, the slope of a secant line, gives us the slope of a tangent line. They're two statements that are exactly the same. We did write that down in 2.1 if you want to revisit that. That's exactly what we're doing here. This is a secant line. We're computing a limit on the secant line. So this is telling us what the slope of the tangent line is on this function x to the 1/3. So I'll just rewrite this here. This applies to this example, but it's general, so it applies to any example. If I compute the limit, we'll just use x. Here we're using h, but it doesn't matter. If I compute a limit on the slope of a secant line, it's going to give me the slope of the tangent line at or near x equals to 0, or a, sorry. The other interpretation, remember secant line, tangent line, that's a mathematical thing. Secant line, the slope of the secant line actually is an average rate of change. So if I compute a limit, again, I'll just use x. It could be t, h, w, whatever. If I compute a limit on the average rate of change, the slope of the secant line, that will give me an instantaneous rate of change. Sorry, that's... again, what we have, the limit on the slope of the secant line being infinity, tells us that the slope of the tangent line on that function at 0, right, because we're getting closer and closer to 0, it's not just because h is approaching 0. The fact that h is approaching 0 is simply allowing the second point to get closer and closer to the point at the origin. So on the graph of x to the 1/3, these infinities we're seeing is the slope of the tangent line. So that's just a shorthand interpretation of the result. This is the slope of the tangent line on this function at the point 0, 0. It's true for both. And for this one. So I know it's kind of a convoluted way to look at that, but that's what we're doing. And I think really the importance of this exercise is, again, to remember what we wrote down here as a general statement right here. And as we've seen, tangent lines can have a slope of infinity, if you will. If a line has a slope of infinity, what kind of line is that? It's straight up and down, it's vertical, right? Because let's look at the graph. So it doesn't look weird right here, right? But once we get closer to it, then we start to see sort of that extreme behavior of that flattening out, if you will. And so if we're approaching, on this function, if we're imagining, at this point here, we're imagining this tangent line, the line that touches at a single point. As we get closer and closer to 0, our work says that the slope of that line should become infinite, which means it just becomes more and more vertical. And you can totally see that here, right? Like it's pretty much vertical right there. From this direction as well, you get a negative slope, that's still positive. So it's all of these are positive approaching a vertical line, a positive infinity. All of these slopes here are positive approaching a vertical line, positive infinity. So that's what that work has shown. I hope that makes sense. If it doesn't, I usually don't have test questions that are that in depth, but I at least wanted to mention the secant tangent line instantaneous average rate of change thing again, and we will see vertical tangents in the future. So does anyone have any questions on that example? All right. So I think it's a good place to stop. Make sure you're starting your homework and let me know if you have any issues. See ya.